Okay, we're going to take a look at laws of logarithms now. That will also include expanding and combining logarithmic expressions and changing the base formula. You'll notice that a lot of these are having to do with remembering that the log of something is an exponent. So it's the same properties as the laws of exponents. Number one, if you take the log base a of a times b, you're adding the log base a of a plus the log base a of b. Just like you're adding exponents when you're multiplying the same base in the laws of exponents. And likewise, the division a over b is going to be the log base a of a minus the log base a of b. And the log base a of a to the c, you're going to bring that c down in front, and you're actually going to multiply the c times the exponent. So when you're evaluating each of these expressions, let's take a look at how we will do that. The first one, since you're adding, you're going to multiply the two numbers, so 2 times 32, and you'll get the log base 4 of 64, which is 3. Subtraction tells us that we're going to divide the 2, so we'll have log base 2 of 16, which we know would be 4. Here I have the negative 1/3 in front of log of 8, and notice there's no base, so that tells us that it is a common log. This would be the log of 1/2. And we can get approximate to this, so we have negative 0.301. Now when we're expanding and combining logarithmic expressions, we're going to use the laws of logarithms to allow us to write the logarithm of a product or a quotient as a sum or a difference. And this process is called expanding a logarithmic expression. Here we're going to use the law of logarithms to expand each of these. Notice the first one we're multiplying. The second one we're multiplying two different bases, but they're also raised to a power. And then the third one we have multiplication in the numerator over the cube root of c. So the first one we simply will expand to add the log base 2 of 6 plus the log base 2 of x. The second one, our first step, will be adding log base 5 of x cubed plus log base 5 of y to the 6th, but we have one more step here. We'll bring those exponents down in front of the logs. This one we have a few steps. First we're going to separate it to subtraction as shown by the fraction. Then we can separate the first one to ln A plus ln B. Remember, natural log of A plus natural log of E would be a log base E. Just a reminder there. And then we're going to change to C to the 1/3. And we'll have to move that 1/3 down in front in the next step. So laws of logarithms also will allow us to go backwards the process of expanding was done, so we can write the sums of differences as a single log. Here, if we take a look at this, we have the logs, and the one thing you want to check is that this is a common logarithm. How do I know that? Because I don't have a base written here, so that would tell me that this is a log base 10. And the first thing we need to check is that this is the same, and it is. So we can go backwards and take the 1/2 and put it on as an exponent, and the 3 and put it on as an exponent. And then the next step would be multiplying the 2 together. Logarithmic functions are also used to model a variety of situations that involve human behavior. So one such behavior is how we forget things we have learned. Oh, I can say that. For example, if you learned algebra of a certain performance level, we'll say at 90% of the test, and you don't use it for a while, how much will you retain after a week, a month, or a year? Now, here we go. Hermann Ebbinghaus, which is a German name, studied this phenomenon and formulated a law to describe it in this next example. The task is learned at the performance level p sub 0. Then after a time interval, you would have your p sub 0 minus c log of t plus 1, where the constant c depends on the type of task and t is measured in months. So you're going to want to solve for p. So if your score on the history test is 90, what score would you expect to get on a similar test after 2 months or after a year? And we're going to assume that C is equal to 0.2. So first we're going to combine the right-hand side, move the C up top, and then we're going to show the division. So we have the log on both sides, so we can then, because log is a 1-to-1, we can set one side equal to the other. And here P will equal 90 and C will equal 0.2 and is measured in months. So when we plug this in, we will get 72 after 2 months, and after 1 year, 54. So you're expected to have scores in 2 months of 72 and 54. Now sometimes you're going to want to change a base, and so we're going to take a look at the change of base formula. Suppose we're given the log base a of x and we want to find log base b of x. So we're going to let y equals log base b of x. And we'll write this as an exponential form to take the logarithm with the base a of each side. So we're talking about the second step here, where we take the log base a on each side. And now we're going to move the y down to the front. And we can divide both sides by the log base a, and then this is what we would do to change our base. So again, here's our formula. The log base b of x would equal the log base a of x over the log base a of b. So if we take a look and we put x equal to a, then the log base a of a would equal 1. And this formula would then become this. log base b of a is equal to 1 over the log base a of b. So let's look at this. Change the base formula and common or natural logarithms to evaluate each logarithm to 5 decimal places. We want to use the change of base formula with b is equal to 8 and a is equal to 10. Because if we have the common log, then we can put that in our calculator. So we have the log base 10 of 5 over the log base 10 of 8. And again, we're changing this to a common log, and that way we can put it in our calculator. And we can use the change of base formula with b equals to 9 and a equals to e for the natural log. So we'll have the log, or the natural log of 20 divided by the natural log of 9.